Hello and welcome to this M3 past paper. This was the 2023 January paper. You were allowed a calculator, the formula booklet, and an hour and a half. Jumping straight in, here we've got a shaded region bounded by the axes, line x equals 1 and the curve. It's rotated through 2 pi radians about the x-axis to form a solid revolution, which is used to model a uniform solid S. Show using the model and algebraic integration that the volume of S is 17 pi over 6 meters cubed. To do this, we're looking at this bit of line here, which is obviously y, rotated about the x-axis like this to form a disk. The area of that disk, pi r squared, is pi times y squared, because y is the radius of that disk. And then to get the volume, we are going to sum up all of those disks from 0 to 1. So we've got pi y squared dx, where delta x is the infinitesimal width of each cylindrical disk going along from 0 to 1. So that's the formula we need to use for part A. V is equal to integral 0,1 pi y squared dx. We put in y, which is 1 plus root x, therefore y squared is 1 plus root x, 1 plus root x, and that gives us 1 plus 2 root x plus x, or in index form, x to the half. There. So this is what we are integrating, and I can pull the pi out the front because that is a constant. So we've got 1 plus 2x to the half plus x dx, and that gives us x plus, increase this, 3 over 2, and that's 2 over 3, therefore 4 over 3 because of the 2 that's already there, plus x squared over 2 from 0 to 1. The 0 here is very easy, that's just 0. So you end up with pi lots of 1 plus 4 over 3 plus 1 over 2 minus a big fat 0. Simplifying that, we do indeed get pi times 17 over 6. So that's 17 pi over 6 meters cubed. We know the units because we are told on the graph that the unit of length on each of the 2 axes is 1 meter. So that's part A done. Part B is to find the centre of mass of S. Now we're told it's 49 over 85. We're going to need to find that. So from our picture here, what we're doing is something very similar. We're taking the disk, and the centre of mass, because it's a disk, it's symmetrical, so the centre of mass is at its centre here on the axis. So as we go to the next disk, which is, let's say, this one here, as we continue down, that centre of mass of this one is here, the distance x away from O. So as we go, we're taking the volume of each one times by the distance away, and when we sum those all up, that must equal the total volume times by x bar. Now we know what the total volume is, we've just found that out in part A. So that's 17 pi over 6 times x bar, and then we want the sum, i.e. the integral, of pi y squared, the volume, as before, but times x dx from 0 to 1. So x bar is equal to 6 over 17 pi, if I bring that on the other side, integral from 0 to 1 of pi y squared x dx. And this is the formula that I'm using for part B. I've tried to show it there with the graph on the screen, but really should have put all of that down here for my examiner. Let's just put x bar is equal to 1 over volume integral 0 to 1 pi y squared x dx. Well, we've still got y squared is equal to 1 plus 2x to the half plus x. And the volume is what we just found, 17 pi over 6. So we've got 6 over 17 pi, and the pi inside the integral can come out as well, and they cancel. 0, 1, x plus 2x to the 3 over 2 plus x squared when I multiply the y squared expression times by the extra x in here. So now we are integrating this, and that gives us x squared over 2 plus x to the 5 over 2, 4 over 5, plus x cubed over 3. And again, all those lovely zeros on the lower limit there makes this a little bit easier. So we've got 6 over 17 times by 1 over 2 plus 4 over 5 plus 1 over 3 minus 0. And that bracket there gives me 49 over 30. We need to multiply that by 6 over 17. And that gives us 49 over 85, which hopefully was the answer they wanted. 49 over 85, centre of mass, so our units there, meters. Part B finished, question 1 finished. On to question 2. A light elastic string AB has natural length L and modulus of elasticity 2mg. The end A is fixed, the other end B is attached to a particle of mass m, so this has weight mg. The particle is held in equilibrium, that's nice, everything is balanced, with the elastic string taut and horizontal by a force of magnitude F. The line of action of the force and the elastic string lie in the same vertical plane. The direction of the force makes an angle alpha, where tan of alpha is 3 over 4, with the upward vertical as shown in the diagram. Okay, so find in terms of L, the natural length, the length AB. So AB is the natural length, say that's here maybe, plus the extension x. And I can split my force here into two components. So we've got F cos alpha, F sine of alpha, and then of course in the string we've got tension this way. So what I'm going to do is find x, the extension, by resolving vertically to find force in terms of mg, and then use that when I resolve horizontally, knowing also that tension in the string is lambda x over L. So resolving vertically, we've got F cos alpha must equal mg, so F is equal to mg over cos alpha. We know lambda is 2mg, so now when I resolve this way, we get F sine alpha is equal to tension, and we know tension is 2mgx over L. But we also know F in terms of alpha and mg from resolving vertically, so let's change that into mg over cos alpha times sine alpha, and you can see here where our tan alpha is going to come in. So we've got sine over cos is tan alpha, we've also cancelled m and g, so that's 2x over L, so x is equal to L tan alpha over 2, and tan alpha we've been told is 3 over 4. So that is 3L over 8 for the extension. But don't stop there, because we didn't want the extension. What we wanted was AB, the total length from A to B. That is the natural length L plus the extension. So AB is equal to L plus 3/8 of L, and that's 8/8 plus 3/8, which is 11/8 of L. that is the length of AB, and that was a relatively quick question compared to the first one. That's all finished. On to question 3. Okay, this looks quite interesting. A square ABCD of side 4A is made from thin, uniform cardboard. I love this word uniform. The center of the square is O. A circle with center O and radius 7A over 4 is then removed. We can see all of this in the diagram to form the template T. Right conical shell with no base has a radius the same. Perpendicular height 6A, we can see this in the other diagram. The shell is made of the same thin uniform cardboard as T, that's good as well. The shell is attached to T so that the circumference of the end of the shell coincides with the circumference of the circle to form the hat H shown in figure 4. Okay, so we've got a bit of card on the left, a square with a circle cut out of it, and a conical shell fitted onto that to make a hat. We're also told the surface area of a right conical shell is pi RL. Show that the exact distance of the center of mass of H, the hat, from O is this horrible looking fraction. Okay, that's part A. Let's deal with this first. So we're doing a center of mass question. So we're doing the mass of part 1 times by the center of mass from O plus mass of part 2 times by its center of mass is going to have to equal the total mass times by the total center of mass of the shape H. So it's not dissimilar to question 1, but we're not integrating, we're just going to add the two pieces together. So what we need to know, remember these are relative masses, so we're not actually going to calculate the mass as such, instead we are calculating the area. And because it's all made from the same thin uniform cardboard, the area will be relative mass. So what we need is the area of the shape T, so we're going to need the area of the square, so that is 4a squared, 16a squared. We're going to need to know the area of the circle, pi r squared, which is pi times 7a over 4, that's not so nice, 49a squared over 16. So the area of T, this shape shaded, is 16a squared minus 49a squared pi over 16. That will be the M1 in my little sketched out table down here. We're also going to need to know the area of the cone, that's sort of M2 in my little table here, and we're told that the surface area is pi RL. So this one here, the area of the cone shape, is equal to pi RL, except we don't know L yet. We need to know this here, and we can do that using Pythagoras because we're given that this is 7a over 4, and of course the height is 6a. So L squared is equal to 6a all squared plus 7a over 4 all squared, 36a squared plus 49a squared over 16. And that, thankfully, is made up of perfect squares. We've got 6 to 5a squared over 16. So L is 25a over 4. So pi RL, remembering that we also know R here is 7a over 4, is pi times 7a over 4 times L, 25a over 4. In the exam, it's fine for you to do work on the diagrams. Obviously, some of this perhaps I would have done on the paper if I could see the diagram and where I was writing at the same time, because on the screen there is the bulk of the preparation work ready to put in. So we've got this little idea. Mass 1 is the relative mass of T, so the area of T, 16a squared minus 49a squared pi over 16. We're going to have that here, 16a squared minus 49a squared pi over 16, and that needs to be multiplied by the coordinate of the center of mass from O. But if we look at this hat on the right here, we can see that the center of mass of that is going to be at O. So the distance there is a 0. That's very nice. That will help when we evaluate this. Then the relative mass of part 2 is the cone. The relative mass is the expression we've got up here. That's 175a squared pi over 16. And that needs to be multiplied by the center of mass coordinate from O of the cone. Now if you forget where that is, don't panic, because that's given to you in the formula booklet. And that is given as 1/3 of the distance from the center point here to the vertex. So 1/3 of this 6a here is 2a. So that's the coordinate of the center of mass of the conical part. So that's 2a there. And then all of that has to equal the total relative mass. So we've got 16a squared minus 49a squared pi over 16 plus 175a squared pi over 16 times by x bar, the coordinate of the center of mass of the whole shape. So this is our equation. First, let me quickly simplify this. That gives us 63 over 8a squared pi, those two terms there. And this bit obviously just gives us a big old 0. So we've got 175a squared pi times the 2a, so that's a cubed. And instead of over 16, the 2 there cancels to make 8. And on the right, 16a squared plus 63a squared pi over 8 x bar. Now before we go any further, let me factorize out a squared. 63 pi over 8 x bar, because that will cancel very nicely with the cubed there. So we've got 175a pi over 8 lots of 16 plus 63 pi over 8 equals x bar. So there's an answer for the center of mass, but it's given to us in a particular format, so let's just check. So we need to put that, was it an 8? Yeah, we need to put that 8 into the brackets. 8 times 16 is indeed 128, and of course that cancels with the fraction there, and that should now agree. 175a pi, or pi a, 63 pi plus 128. Maybe I should just finish this off. 175 pi a over 63 pi plus 128 as required in the question. Part B. A fixed rough plane is inclined to the horizontal at an angle alpha. The hat is placed on the plane with ABCD, that's the square bit, in contact with the plane, AB parallel to the line of greatest slope. The plane is sufficiently rough to prevent the hat from sliding, so it definitely does not slide. Given that it's on the point of toppling, find the exact value of tan alpha. Okay, let me quickly sketch this out. We've got a plane, it's rough, it won't slide. The hat is on the plane, something like this. It's on the point of toppling, which means the center of mass, wherever that is here, this is a terrible diagram, is on top of the last point of contact. So although it doesn't look it, that should be vertical. This we know, and this we know, so we should be able to find, if I draw it slightly better over here, this distance here is half of the square. So from the edge of the hat to the center is 2a. So this is a 2a distance, that's this bit here. The center of mass is 175 pi a over 63 pi plus 128. That's this distance here, up from O, here on my diagram. And we want to find alpha, or tan alpha, and alpha is inclined of the plane to the horizontal. Okay, so this is alpha here. Relating that to my diagram, that puts alpha here. So tan of alpha is equal to opposite, 2a, over adjacent, 175 pi a over 63 pi plus 128, and that of course comes up in the numerator. We've got 63 pi plus 128 over 175 pi a. The a's cancel. That gives us 126 pi plus 256 over 175 pi as the exact answer for tan alpha. Part B finished, and the question 3 finished. On to question 4. A particle P is moving along the x-axis at time t seconds, where t is between 0 and 2/3. P is x meters from the origin, moving with velocity v in the positive x direction, where v is given as this. When t is 0, P passes through O. So when t is 0, x is 0, being measured from O. Find the value of x when the acceleration is 2, 4, 3. All of this is happening in the positive x direction. So here's O, and we're going to need an expression for A in order to use that information they've given us. So if we know v is 2x plus 1 to the 3 over 2, A is equal to v dv by dx. dv by dx, then differentiate this, we get 3 over 2, 2x plus 1 to the 1 over 2 times by the derivative of the thing in the brackets. That cancels, so we get 3, 2x plus 1 to the half. If we multiply that by v, which is 2x plus 1 to the 3 over 2 times by 3, 2x plus 1 to the half, they combine to give us 3 lots of 2x plus 1 all squared. That is A, and we're told that A is 243, and if we divide that by 3, we get the very nice square number 81 on the right. We're going to square root that to give 9, and we know that x is positive, so I'm not going to worry about the negative solution to the square root there, and that will be 8 for 2x. X is equal to 4. Part B, find v in terms of t. So we know v is equal to the thing at the top of the screen, 2x plus 1 to the 3 over 2. But we don't know v in terms of t, and that's what the question wants us to find. To do this, what I'm going to do is find this. I'm going to integrate by separating the variables to find x in terms of t, and then differentiate again with respect to t to find v in terms of t. So separating my variables gives dt 2x plus 1 to the minus 3 over 2 dx. So we get t is equal to minus 2x plus 1 to the minus a half divided by the derivative of that, which is 2 plus c. So we get t equals minus 2x plus 1 to the minus a half plus c. And to double check, I just take a moment to differentiate that in my head to make sure it gets us back to where we started. I think it does. We need to deal with this boundary condition though, the c. We know from the question up here, t equals 0 when x equals 0. So putting that in, 0 must equal minus 0 plus 1 is 1 to the minus a half, plus c. 1 over root 1 is obviously 1. Bring it onto the other side and we get c is equal to a 1. So t is equal to minus 2x plus 1 to the minus a half plus 1. Now I'm going to rearrange this so that we get x in terms of t, and then I can differentiate with respect to t. So we get t minus 1 minus 2x plus 1 minus a half. That's silly, I should have taken this on the other side. Let me do that instead. And then this becomes 1 minus t. And then we're going to bring the index, so that's minus 2 in order to make this 2x plus 1. And I'll leave that in index form for now because we're going to differentiate. So we've got 1 minus t to the minus 2 minus 1 for 2x, and then a half for x. Now dx by dt, which will give us v in terms of t, is going to be minus 2 over 2, 1 minus t to the power minus 3. So that half disappears to 0 when we differentiate that, and we also have a minus 1 coming out of this bracket. We need to multiply by the derivative of the expression in the bracket. So all of that, if that cancels and that cancels, we end up with 1 minus t to the minus 3, or perhaps in a slightly nicer 1 minus t cubed. And that is v in terms of t. There's a lot of work to do that, given that we already had v in terms of x, but that is the end of question 4. Question 5. A particle p of mass m, let me put the weight on straight away, mg, is attached to one end of a light inextensible string of length a root 3, the other end attached at point A. It's also attached to the end of a second light inextensible string of length a, and the other end attached to point B. So we've got two separate strings. B is vertically below A, and AB is equal to little a. The particle P moves in a horizontal circle where O is vertically below B. It also moves with constant angular speed omega, with both strings taut. So we've definitely got a T1 here and a T2 here, as shown in the diagram. Show that the upper string makes an angle of 30 degrees and the lower string makes an angle of 60 degrees with the downward verticals. Let me call that alpha, beta. So alpha should be 30, beta should be 60. Quick glance at the marks. That's only worth 2 marks, so my initial thought I think is probably okay, and that is that we can do this just using geometry, because we've got an isosceles triangle here, because we know that from A to B this is little a, but the length of the string from B to P is also little a, and we know that this is a root 3, and we're trying to find this, so that says to me cosine rule. So in order to use that alpha there, we would have a squared is equal to a squared plus a root 3 squared, which would be 3a squared, minus 2 lots of a times a root 3 times cosine of capital A, which would be alpha. I can cancel these a squareds and bring this on the other side, make it positive, so we've got 2 root 3 a squared cos alpha is equal to 3a squared, and I should have done this down below. I'll just copy that down here. Okay, continuing on, we can cancel these a squareds as well. Cos alpha is equal to 3 over 2 root 3, or root 3 over 2. Alpha then is the inverse cosine root 3 over 2, which is indeed 30 degrees. So we've got 30 degrees for alpha. Now what I would do is I would not do all of that again, because if I sketch out a second little diagram here, this is 30, we know that now for sure. This vertical here then, because this is vertical, they're parallel, this is also 30, and because this triangle is an isosceles triangle, this is also 30, which means the right angle that this makes coming across here is also 30. We know B is vertically above O, which means this must be 60. Again, I'll bring that down maybe here. Therefore, beta equals 60 degrees. Hopefully that's enough for the examiner to allow me that mark. There's only 2, so although they've given the answers, I suspect that is enough. Part B, show that the tension in the upper string is this expression here. So this is the bulk of the marks. Coming back up to the diagram, we've got T1 and T2. T1 is what we want, but T2 is going to be involved as well. We're going to make 2 equations here. We know, if I put this on here now, that this is also alpha, 30 degrees, and that this is beta, 60 degrees, like so. So if I resolve vertically, we've got T1 cos 30. Start putting that down here. T1 cos 30, resolving vertically, plus T2 cosine 60 must equal mg, the weight vertically downwards. But we need a second equation, because there are 2 things there we don't know, T1 and T2. Our second equation is going to come from the fact that we've got circular motion. So T1 sine of 30 plus T2 sine of 60 is producing this inwards force F, which is producing our acceleration that is moving the particle around the circle. So T1 resolving inward, we've got T1 sine of 30 degrees plus T2 sine of 60 degrees, and this is F equals MA, but instead of MA, I'm going to be using A in terms of omega, and that will give me mR omega squared. And let's quickly point out that we know R as well. R in terms of the distance here, the radius of the circle, that is equal to A cos of 30, which is root 3 over 2A. So that's m root 3 over 2A, not A here, obviously. This is acceleration in F equals ma, and here the A is the distance or the length of string PB. And now we've got omega squared. So T1 sine 30 degrees plus T2 sine of 60 degrees equals m root 3 over 2A omega squared. So now we've got 2 equations, both involving T1 and T2. So we can now put these together. We want T1, so let me rearrange the one on the left here to give T2, and then we can substitute. Cos 60 is equal to mg minus T1 cos of 30. And we know what those are, so let me put that in. That's a half, so that's T2 over 2, and this is root 3 over 2 T1. Multiply everything by 2, gives us 2mg minus root 3 T1 for T2. Now I can substitute that into the horizontal equation to give T1 sine of 30, so that's a half again, plus T2, but we're going to substitute 2mg minus root 3 T1 for T2, and then sine of 60, which is root 3 over 2. And that has to equal m root 3 over 2 A omega squared. Rearranging this to give T1 in terms of everything else. First of all, we can cancel all halves. That's nice. T1 plus root 3 or 2 root 3 mg minus 3T1 is equal to root 3 ma omega squared. Rearranging this a little bit gives me 2T1 is equal to 2 root 3 mg minus root 3 ma omega squared. We can factorize out root 3m for 2t, and that gives us 2g minus a omega squared, and then bring the half. So we've got a half root 3m 2g minus a omega squared, and hopefully that matches what we needed. Half m root 3, yes. 2g minus a omega squared, yes. Except they've written m first. There we go. T1, the tension in the upper string. Part C, show that omega squared must be between these two values. To do this, we are recognizing that T1 is a value. Both strings are taut, so T1 must be greater than 0, and T2 also must be greater than 0. That's where we're going to start with this question. So we've got T1 already, so we know T1 must be greater than 0, therefore this expression, a half m root 3 2g minus a omega squared must be greater than 0, so 2g minus a omega squared must be greater than 0, 2g must be greater than a omega squared, 2g over a must be greater than omega squared. Or more to the point of what they've got, omega squared is less than 2g over a. But we also need to know T2, and we're going to use this expression here, knowing T1. So we've got 2mg minus root 3 lots of T1, which is a half m root 3 2g minus a omega squared, like this. Tidying this up, we get 2mg minus 3 over 2 m 2g minus a omega squared. And this thing must also be greater than 0 if both strings are taut. So 2mg, let's open these brackets as well, that gives us minus 3mg plus 3ma omega squared over 2 must be greater than 0. mg on this side, 3ma omega squared over 2 on this side, m's cancel, we get 2g over 3a omega squared must be greater than this. Therefore, we've got 2g over 3a omega squared must be greater than this, but from the previous one we also said omega squared must be less than 2g over a. And again, hopefully that matches what they've told us. 2g over 3a, 2g over a. Yes. That's part C finished. Question 5 finished. On to question 6. Here we have a small, smooth ring R of mass m threaded onto a smooth wire in the shape of a circle. Center O, radius L. So from here, each of these is L. The wire is fixed in a vertical plane. The ring R is attached to one end of a light elastic string of natural length L. So in its current position, the extension is also L from A up to where the ring is at the top of the circle. And modulus of elasticity mg. The other end of the elastic string is attached to A, the lowest point on the wire. The point B is on the wire and OB is horizontal. The ring R is at rest at its highest point. The ring is slightly disturbed from rest and slides along the wire. at the instant when r reaches point B, the speed of r is v. So at this point here, the speed is v. The magnitude of the force exerted on r by the wire is n. So at this point, the string is here, and its length is root 2L, using Pythagoras here. And given that both the ring and the wire are smooth, although the tension at this point is acting this way, N is acting horizontally. Okay, but what is the question? Show that v squared equals 2gl root 2. Okay, we need the velocity at B, so I'm going to use an energy approach. We'll consider at the top of the circle, the kinetic energy is 0, the potential energy is mgh, and the elastic potential energy is lambda x squared over 2L. Then we'll do the same thing at B, and we should be able to equate them because there's no friction involved. So at rest, we've got kinetic energy, 0, gravitational potential energy, mgh, and elastic potential energy, lambda x squared over 2L. Now at that point, h, if I take A as my 0 level, at this point here, then h up at the point here is L plus L 2L. So we've got mg times 2L here. And x, if we go back up again, given that the natural length of the string is L and it's stretched up another L, x is also equal to L. So we've got lambda, no, wait a minute, we know lambda is mg, so we can write this as mg L squared over 2L, which equals mg L over 2. So our total energy in the system is 2mgl plus mgl over 2. That's 2 plus a half, so that's 5 over 2 mgl. Now that total must stay the same because there's no friction, so the energy is being conserved when we get to point B, where we do have kinetic energy. So at B, kinetic energy is equal to a half mv squared, which is how we're going to find RV. Gravitational potential energy, compared with A, the vertical height of this is L, so that's mgl, and the elastic potential energy is the same as it was, lambda x squared over 2L, but now x is different. So here we've got root 2L as the distance, but that means the extension is root 2L minus the natural length L. So we've got root 2 minus 1 lots of L. So put that down here. Lambda mg again. Root 2, let me put it like this, minus 1L, all of that squared over 2L. Root 2 minus 1 squared is equal to 2 minus 2 root 2 plus 1, 3 minus 2 root 2. So this becomes mg 3 minus 2 root 2 times L squared, but we've got an L on the bottom, so I'll just put L there and a 2 there. So our total energy at B is given by a half mv squared plus mgl plus mg 3 minus 2 root 2 L over 2. And that must be the same amount as we had here, 5 over 2 mgl. So this thing, if I write it out again, get rid of these brackets, so that's plus 3 over 2 mgl minus 2 root 2 over 2 mgl must equal 5 mgl over 2. And you can see they've all got this mgl, or most of them, not the half mv squared, but they do all have m, so we can cancel m's, get rid of them. And then we've got lg plus 3 over 2 lg, that's 5 over 2 lg, so actually this whole term cancels with these two. So we end up with a half v squared is equal to 2 root 2 gl over 2. Now the halves can cancel, and we end up with v squared is equal to 2 root 2 gl, which hopefully 2gl root 2, yes. So we've shown that v squared is this expression. Now we need to show that n, the force, the horizontal force acting on the ring from the wire, we need to show that that is half mg 5 root 2 minus 2. To do this, we're going to consider our tension here and realize that because the L and the L, this little triangle we've got going on here, this must be a 45-degree angle. So our horizontal force in this way is t cosine 45, or t sine 45. Now that might not seem to help us very much because we don't know t, but we do know that tension is equal to lambda x over L. That's mg, and x at this point is root 2 minus 1 lots of L over L. And if this were in equilibrium at this point, that would be quite useful, because multiplying this by cosine 45 would give us n. But it's not in equilibrium. This is moving, and it's moving in a circle. So we've got an inwards force is equal to mass times acceleration. Now acceleration, I would normally write r omega squared, but we've been given v, not omega. But you know that there's a connection, so we can substitute and have mv squared over r. And that's our resultant force, in this case t cosine 45 minus n. So putting all that down here, part B, we've got F is equal to ma, which is equal to mv squared over r, F t cosine 45 degrees minus n is equal to mv squared over r. And hopefully you can already see how useful part A is, because we can substitute v squared for the expression we found in part A. And t was mg root 2 minus 1 times by the cosine of 45, which is root 2 over 2, minus n is equal to m times v, 2 root 2 gl over r, the radius of the circle, which we know is L. Putting all of this together then, n is equal to mg root 2 times root 2 over 2, just gives us mg, minus mg times root 2 over 2, so that's root 2 mg over 2. If that's not clear, I've just expanded the bracket on the left there. Then we've got minus 2 root 2 mg L over L, so that cancels, we don't need that L. Cross that out. That simplifies to minus 5 root 2 mg over 2. How do we need this to look? Into brackets 5 root 2 and a 2, so we take out a half mg. That becomes 2 minus 5 root 2. Now that does not agree with what we've been given here, and that's because I should keep in mind this little word here, magnitude. Now it might be that I've messed up part of my direction somewhere, but at this point it doesn't really matter, because all I can do is just put a magnitude there, and I can see quite clearly that this is going to be a negative value, because the 5 root 2 is bigger than a 2, so the absolute value of this, or the magnitude of this, is going to be 5 root 2 minus 2 in the bracket there like that. And that should satisfy the examiner, even if I've made a minor error with my directions, although I don't feel like I have. Drop a comment in the comment section if you can see where I went wrong there. But that's the end of question 6. On to question 7. 2 points A and B lie on a smooth horizontal table where AB equals 4L. Particle P of mass m is attached to one end of a light elastic spring of natural length L, modulus of elasticity 2mg. The other end of the spring is attached to A. Particle P is also attached to a second light elastic spring of natural length L, but different modulus of elasticity. The other end of the spring is attached to B. Okay, let me get these modulus of elasticities in the right place. So it's 2mg on this side and mg on this side, but both of them have natural length L. The particle P rests in equilibrium on the table at the point O. So this is our equilibrium point, and if that's 5/3, then this is 7/3 of L. The particle P has moved a distance 1/2 of L along the table from O towards A. Okay, so it's not actually at that point, it is, let's say it's here, where this is 1/2 L. That means this distance is now 7/6 of L, and this distance from B to that point is 17/6 of L. From here it's released from rest. Show that P moves with simple harmonic motion of period t. So at this point we've got an amplitude of 1/2 L, if that helps us. And we need to show that t is 2 pi root L over 3g. This is a fairly standard question. What we need to be careful of, though, is that we take our extension and we don't get it mixed up with the displacement from O. And unlike the previous question, I need to be very careful with my directions here, not to get them wrong. I can't fix it with a magnitude sign later. So from here, the extension, which I'll call E instead of X, allowing X to be the displacement, the extension of the spring on the left is equal to 2/3 of L minus X, the displacement. Initially that displacement is 1/2 L, but once it's released, that's a variable. On the other side, the spring from B, the extension here, again from natural length L, up to O is 4/3 of L, and then plus whatever that X is. Again, initially it's 1/2 L, but that will change once the particle is released. So what we're doing here is we're building up enough information to find T2 going this way in this spring and T1 going this way in this spring, so that we can apply F equals ma, but so as not to get confused with the A that I might want to use for amplitude that I've got on my diagram already. I'm going to use the normal simple harmonic motion notation of x double dot, and F will be, remembering that we're always taking the displacement direction to be the positive, so from where it is now, this direction to the left is positive, so it will be T1 as positive and T2 will be negative. Mx double dot, also remembering that tension is lambda x over L, but again, so as not to get confused with the x that I've used for displacement, I'll keep that E as my extension, like so. That's a lot of information on the diagram. Let me get writing some of this down here. So we're using F is equal to ma, F is equal to mx double dot, T1 minus T2 is equal to mx double dot, and then T1 is lambda E, lambda for T1 is 2mg, times the extension, which was 2/3 of L minus x, and all of that lambda E over L, minus T2, lambda for T2 is mg, times by E for T2 is 4/3 of L plus X. And the natural length of the 2 is the same, that's L as well. And that has to equal mx double dot. Now expanding these out, we've got 4/3 mgl over L, so I'll split the fraction as well and cancel that, minus 2mgx, and this part is still over L. From the second one, we've got minus 4/3 mg, and again the L will cancel for that one, minus mgx over L, and as often happens here, we've got some lovely cancelling. We get minus 3mgx over L is equal to mx double dot. The m's cancel. I write the x double dot on this side. We get to minus 3g over Lx, which is a simple harmonic motion with omega squared equals 3g over L, because simple harmonic motion is x double dot equals minus omega squared x. But it didn't want omega, it wanted t. T is equal to 2 pi over omega, and omega we don't actually have, we've got omega squared, 3g over L, and if we want to divide by that, then we can flip that upside down, 2 pi root L over 3g. 2 pi root L over 3g, which matches what they've got in the question. Part B, find in terms of L and G the speed of P as it passes through O. Okay, simple harmonic motion ideas here are that when you're passing through your equilibrium point, that's the maximum speed. Hopefully you also remember an equation here that will help, namely that v squared equals omega squared a squared minus x squared. We know omega squared is equal to 3g over L, and at O, the displacement from O is obviously 0. So v squared is equal to omega squared a squared 3g over L times a, and a is the amplitude that I marked on the diagram earlier, which is a half L. L squared over 4 when we square it. Let me put that here. A is equal to a half L. So one of those cancel, and we get 3gl over 4. Was it v squared that we wanted, I think? No, the speed, v. So square root this, we get root 3gl over 2. That's part B finished. Part C, find in terms of g the maximum acceleration of p. Well, we've done most of the work for this, that's why this one's only 1 mark as well. Here we've got acceleration is equal to minus 3g over Lx minus 3g over Lx, and this is maximum when x is at its maximum displacement, which is the amplitude, which is a half L again. So we've got minus 3g over L times by a half L, and again L's cancel out, minus 3g over 2, and having said that I shouldn't use or won't be able to use a magnitude symbol, actually I think I probably will here, because our maximum technically would be 3g over 2. For 1 mark, I'll just put a little therefore on that, and that should be okay, because we know with simple harmonic motion it's always acting in the opposite direction to the displacement. Part D, where is it? Find the exact time in terms of L and G from the instant when P is released from rest to to the instant when p is first moving with speed 3/4 root gl. 3/4 root gl. First, let me go back to v squared equals omega squared a squared minus x squared, and we know v, therefore v squared 9/16 gl. I can put that in here. I also know omega squared, if I could remember it, 3g/l, and a is equal to 1/2 L. This will tell us where it happens, and then I can work on when after that. So 9/16 gl equals 3g/l, l/2, or l squared over 4 once we square that, minus x squared. Our g's cancel, and the 3's cancel to give us 3l squared over 16 equals l squared over 4 minus x squared. Rearranging this, l squared over 4 minus 3l squared over 16 gives us l squared over 16. And x is equal to l/4. Now if we remember that x is equal to a cos omega t for simple harmonic motion, starting at one extreme end of the simple harmonic motion, i.e. at a, then we can work out by putting in what we know, l/2 cos omega, I've forgotten again, 3g/l square root t. Then we can work this out because the l's cancel. The 2 over there becomes 1/2. And that gives me the inverse cosine of 1/2, which in radians is pi/3, is equal to root 3g/lt. Therefore, t is equal to pi/3 root l/3g, which is not a very nice answer for t. What did it say in the question? In terms of L and G. Yep, okay, that makes me feel a little bit happier. So that looks like our final answer for the final part of the final question for this M3 paper. So I hope that has been of some help to go through for you.